Hey everybody, my name is Chris and I'm a tutor here at Chegg.com, and I mostly do math and a little bit of computer science. And in this video we're going to do an example with conformal mappings, and specifically we're going to do linear fractional transformations. So before we jump into this example, let's just briefly talk about conformal mappings. So generally speaking, a conformal map in the complex plane is a map that essentially preserves angles. Okay, so a very special important type of conformal mappings is the linear fractional transformation. Sometimes it's also called the fractional linear transformation, but it's just the same exact thing, just with these two words swapped. And a linear fractional transformation has this general form: az plus b divided by cz plus d, where we have the restriction that ad minus bc does not equal 0. And notice also that a, b, c, and d are actually complex numbers, not necessarily real numbers. Okay, so we want to find the linear fractional transformation. In other words, find the function in this form that sends 1 plus I to 0, 2 to infinity, and 0 to I minus 1. So there are a couple different ways we can approach this, and I'll just do one way in this video. And for me, I think the easiest way to start is by saying, okay, we have something that goes to infinity here. So because this sends 2 to infinity, then what we can say is in the denominator, we're going to have z minus 2. So the denominator is going to be z minus 2, because then when z equals 2, we're going to be dividing by 0, which is essentially in the complex plane going to give us, or the extended complex plane, I should say, is going to give us infinity. Okay, so we have that. So far, our conformal map looks like az plus b divided by z minus 2. And yeah, technically we could maybe have like 2z minus 4, that'll also work, but let's just keep this as simple as we can. Alright, so now we have something going to 0, so that also makes things pretty simple for us. So if this map here sends 1 plus I to 0, then what we could say is in the numerator, we can have z minus 1 plus I. Okay, now so far it's tempting to say that we just have z minus 1 plus I all divided by z minus 2, and then we'll say, oh, okay, so we're done. But we're not quite done, because we have the additional restriction that 0 has to go to I minus 1. And if we plug z equals 0 into here, what we're actually going to get is minus 1 minus I all over minus 2, which simplifies to 1/2 plus 1/2 I. And notice that that is actually not equal to I minus 1. So we have a problem here, and it might look like we're stuck, but actually we're not really stuck. So what we can say is that, okay, well, so far we actually have this, where a is some complex constant. Okay, so far we have this. So now we can use this additional criteria here to find out what a is. So let's go ahead and do that. So let's, I guess we'll just move to the next page. So far we have a times z minus 1 plus I over z minus 2. And we know that when z equals 0, we have I minus 1. Is that right? I minus 1? Yes. Okay. So when z equals 0, what do we have in here? Well, we have a times 0 minus 1 minus I over 0 minus 2, which is just going to be a times 1/2 plus 1/2 I. And we know that this is supposed to equal, let's say, negative 1 plus I, so we can keep this in standard form. So really, this might look like there might be no way out here, because we have a times 1/2 plus 1/2 I is supposed to equal negative 1 plus a positive 1 times I. But remember that a is actually complex. So remember that we can actually express a as, let's say, x plus iy. Okay, so if we express a like that, then what we actually have is x plus iy times 1/2 plus 1/2 I equals negative 1 plus I. So now let's go ahead and expand on the left hand side here and see what we get. So we're just going to FOIL this essentially, and then when we do that, we're going to get x times 1/2, that's our f, and then our o is going to give us plus 1/2 times x times I, and then the I is an inner, is going to give us 1/2 y I, and then the last is going to give us 1/2 y I squared, and then we still have equals -1 plus I. So when we simplify this, let's keep the real and imaginary parts together. So I squared is -1, so for the real part we essentially have 1/2 x plus, or excuse me, minus 1/2 y, that's our real part, because the I squared is -1, so plus 1/2 y times -1 becomes minus 1/2 y, so that's why we have minus 1/2 y here. And then we have plus I times 1/2 x plus 1/2 y. Okay, so this came, what I just wrote here came from this part right here. That's our imaginary part with the I over there. Okay, and remember that this equals -1 plus I. So now we can equate the real and imaginary parts to solve for x and y, and then once we find x and y, we'll have a. And then we can simplify a little bit and we'll be done. So here, there are the real parts, and then here are the imaginary parts. And then really, plus I means plus I times 1. So then what we have is this over here. Okay, so let's go to the next page and write down, essentially it's a system of two equations with two unknowns. So we have 1/2 x minus 1/2 y equals -1, oops, and 1/2 x plus 1/2 y equals +1. Just make sure that's correct. Yes, 1/2 x plus 1/2 y equals +1. Okay, so we have a system of two equations with two unknowns, and we just want to solve this. So let's go ahead and add both equations together. 1/2 x plus 1/2 x is just plain old x. Minus 1/2 y plus 1/2 y is 0. That's great. -1 plus 1 is 0. So that gives us x equals 0. Okay, that's great. Now, if x is 0, then we could use either of these equations. Let's use the second one. And we get 1/2 y equals 1, which means y equals 2. Okay? So if y is 2, remember a is x plus iy. So that means a equals x plus iy equals 0 plus I times 2, which is more standardly written as just 2i. So a is 2 times I, and remember, this was our linear fractional transformation we're trying to find. So what we have overall then is 2i times z minus 1 plus I over z minus 2. And of course, we could distribute the 2i and simplify a little bit. And let's, just to keep it in standard form, let's go ahead and do that. So we'll have 2i times z, and then minus 2i minus 2i squared all over z minus 2. So all I did here was distribute the minus sign so that we have minus 1 minus I, and then distribute the 2i to everything. Because note that the 2i is being multiplied by the entire top up here. Okay, so be careful about that. And then finally, I'll write the final answer up here. When we simplify that, minus 2i squared is minus 2 times -1, which gives us a plus 2. So our final answer is going to be 2i times z plus 2 minus 2i, all divided by z minus 2. Okay, so this is the linear fractional transformation that sends 1 plus I to 0, 2 to infinity, and 0 to I minus 1. All right, so this has been an example of finding a linear fractional transformation that satisfies given conditions. I hope you found this video helpful, and thank you for watching.